Okay, so once again, welcome back. And today we will talk about a very popular topic in digital electronics called as universal gates. So there are two types of gates, special gates, which are called as universal gates. What these gates are? First one is NAND gate, and the second one is NOR gate. So out of so many other gates, only NAND gate and NOR gate can be called as universal gates. Now, why are they called as universal gates? The answer is they are called as universal gates because all other basic gates can be constructed using either NAND or NOR gate. So what are the basic gates? The basic gates is a NOT gate, AND gate, NAND even, OR gate, NOR gate, XOR gate, XNOR gate. So these gates can be constructed using only NAND or only NOR. So it means you have to use only NAND gates to create any other basic gate, or you have to use only NOR gate to create any other basic gate. So let us start first by creating a NOT gate. NOT gate is basically an inverter. So we will see now first how NAND can be used to construct a NOT gate. So you see here, this is a two-input NAND gate. Both of its inputs are shorted and it becomes a single input called as A. And the output, as you can see, there is a bubble. That's why it is a NAND gate symbol. Output is Q. So when A is at logic 0, output Q is logic 1. When A is at logic 1, output Q is logic 0. That is how this single NAND gate with both of its inputs shorted together is acting as an inverter or simply a NOT gate. How about using NOR to create a NOT gate? Again, we are using a two-input NOR gate. Both of its inputs are shorted to each other, and we have a single input signal labeled as A. Its output is Q, and this is a symbol of a NOR gate. So when A is at logic 0, output is logic 1, and when A is logic 1, output is logic 0. So this is how you can create a NOR gate, NOT gate actually, using a NOR gate. So this is how we understood we could now create a NOT gate or an inverter using either NAND or NOR. How about we want to make AND gate using only NAND or using only NOR? So to do that, first have a look at this figure. You use a two-input NAND gate. This is the, let's say, gate number 1. You have got two inputs, A and B, and the output here would be, let me write here, the output here would be A NAND B. Remember, it is a two-input NAND gate. So output here would be A NAND B. Now, this output of a first NAND gate becomes an input to the second NAND gate here. This is the second NAND gate. Now, this second NAND gate, both of its input are shorted to each other, and the output is available right over here. And we know that what is the input to gate number 2? Input is A NAND B. That is the output of a first NAND gate. Therefore, output here can be simply an inverter. A NAND B, invert and again invert. Therefore, output would be simply A and B. Two bars are cancelled with each other. Because you see, this second NAND gate is nothing but an inverter that we saw before. So this is how you created a AND gate using only NAND. How about using NOR, only NOR, to make an AND gate? How we do that? We have gate number one. Both inputs are shorted to each other. Input here is labeled as A. Gate number two, both inputs are shorted each other, labeled is B. Therefore, the outputs of these gates 1 and 2, here comes A bar, here comes B bar, because these two are acting as an inverter. Now, output here, Q, would be A bar NOR, actually. This is a NOR. B bar and then bar. Okay, and therefore it becomes, by De Morgan's theorem, A and B after simplifying this expression. So this is how you got to use the NOR gate to make an AND gate. Very well explained. How about now we may want to make a NAND gate using NAND. So nothing to worry about. We have two input NAND gate, A and B. And the output here is simply A NAND B. That's it. How about we want to construct a NAND gate using only NOR gates? So how we realize a NAND gate using only NOR is right over here. You have gate number one, output here is A bar. You have gate number two, output here is B bar. And then gate number three, the output here is right over here, A bar or B bar, and then take a complement, which is nothing but, you can see that we have solved it here. That would be A and B, simply by De Morgan's theorem. Now A and B is the input to gate number 4, actually, because both of inputs of the gate number 4 are shorted. Therefore, the output here, Q, is equal to A NAND B, simply. A NAND B. So you see, we got the NAND implementation done. Now, we have to understand how we can use or construct an OR gate using only NAND. So here, gate number one, NAND gate used as an inverter, output here is A bar. Gate number two, output here is B bar, because gate number two NAND is used again as a NOT gate or inverter. Now this is gate number three, and the output here is A bar, B bar, and NAND of it. And therefore, again, by De Morgan's theorem, this expression can be solved as A or B, simply. Okay, now how about implementing the OR gate or OR logic using NOR? It's very simple. You have used a two-input NOR gate. So output here is A NOR B. Then again an inverter, NOR gate as an inverter, which will take a complement of NOR, making it OR, A or B, right over here. Very simple. Now, we want to implement a NOR gate using only NANDs. So first input, first gate, output here is A bar. Second gate, output here is B bar. Here, the gate number 3, that is the two input NAND. So the output here is A bar and B bar, and then take a complement. That is NAND of it. And this becomes, actually, this expression is nothing but A or B after De Morgan's law applied. Now A or B, A or B is the input to the gate number 4, making the output Q is equal to A or B and take a NOR of it. And that's how we got NOR gate using only NAND gate. How about NOR? Using NOR is very simple. It's just one NOR gate, which is two input NOR gate. Here, the output is Q equal to A NOR B. So this is how we are solving our expressions. How about implementing XOR logic using only NAND? So for that, you can see now gate number 1, the inputs are A and B, and the output right over here would be A NAND B, actually, A NAND B. And now A NAND B becomes input to gate number 2 and gate number 3. Therefore, the outputs here are A and B, A and B, and therefore the Q here would be, let me write here, Q here would be A and B, that is the first gate, and then you have A and B again, and take a NAND of it. So if you see that how it is basically XOR expression, that is A bar B or A B bar. This is how you can simplify it too. So this is an exercise for you. How about XOR gate using only NOR gate? So again here, gate number 1 output would be A bar. Gate number 2 output will be B bar. Here gate number 3, A and B. So it's NOR A NOR B. And here would be A bar, B bar, and take a NOR. So that becomes A and B. And here you would have like A and B, and A or B bar, and then take a bar. So if you solve it, it would be A bar B or A B bar. So try as an exercise for you. Similarly, you have an XNOR. So how would you solve? This is gate number 1. This becomes A bar. Gate number 2. This becomes B bar. And this is gate number 3. So it would be A bar and B bar and then bar. It is A or B by De Morgan's law. Here A and B NAND, and then just take output right over here. So you can see that this is how, if we put in the enough expressions there, we can actually solve this query. Okay, so this is an exercise for you. Try simply imply, not imply. Just put in the gate numbers and write the outputs, and then see how further expressions can be solved. This is also an exercise for you, that just see that how we got it solved from this to this, and how we got solved from this to this. Okay, so if you like this